Okay, I think it's time to start.
Okay.
Welcome to this technical session 10, Soft Matter 2, in the virtual room Palma. We start with the first speaker, Maciej Matica, that will be talking about memory-efficient lattice Boltzmann method for low Reynolds number flows. So you have 20 minutes, 15 minutes plus 5 questions. So I'll give you a sign. I'll let you know when you are at 15 minutes. So the floor is yours. Please go ahead.
Okay, thank you very much. So welcome everyone. I'm very happy to be here today. I was actually dreaming about being on this year's SFD conference for years, but it was always on vacations, so this year was much easier. I was planning to go to Italy. Unfortunately, we're here, but fortunately it goes smoothly. So yeah, I hope you enjoy my talk. So I will be talking about memory efficient lattice Boltzmann method. It's a little bit of changing the usual lattice Boltzmann we are working with in order to get some quite large achievement in the memory consumption of the method. So we will see. We are together with Michał, who has developed a bit at the very end. You will see something about MRT formulation. And the main idea is not ours. It was in the literature for years in many places. People were trying to go into this direction, but we did find some nice results. So let's see. So I'm working with Purs Media. So Purs Media, as you know, are quite large systems with small narrow passages for the flow. So it's a very memory demanding task to go to simulate the fluid directly. Here is an example. It was done with Palabos some years ago with my PhD student Jarek Gołębiewski and Wojtek Sobieski, and we were trying to calculate distribution function of velocity in the porous media like this. So you can imagine how much memory was needed to simulate these systems. Of course, you can always go for large clusters and so on, but yeah, for some reasons and some applications, decreasing memory in lattice Boltzmann may be also a nice goal to achieve. So, okay, so let's go straight and just do lattice Boltzmann without distribution function. So that's the main idea. And how did we find out this idea? So it was in, as I said before, in literature before. So the idea is that if you use the usual standard formulation of BGK, so the one that you all know, so this is the single relaxation time lattice Boltzmann on one slide. So you have the distribution function in the first line, the second is the equilibrium distribution function, and you have the viscosity for the model. So it's BGK formulation. How about this parameter tau, which is used in single relaxation time? So of course, people use different numbers for it. So numerically, this might be below 1 or above 1. It can be also 1. And for some, so physically this doesn't matter, of course, but it changes the properties of the flow, and also changes some properties of numerical properties of the solver itself. But we have our interest is, of course, to calculate the density and the velocity directly from distribution function. So if you take moments of the distribution function, you will get the density and velocity. This we already know. So let's put the relaxation time equal to 1. And now I have to explain to all of you that it's not just from the sale. So people use tau equal to 1 in many papers. You may find that it's sometimes it's even of the first choice. Some people analyze the numerical stability of lattice Boltzmann for different tau numbers, and not only stability but also accuracy of it. So we have, of course, did this research a bit, and tau equal to 1 doesn't seem to be very special. I mean, in case of stability, there are other numbers numerically which are better. But anyway, if we put tau equal to 1, algorithmically, the algorithm simplifies very much. So you have the distribution function, the evolution of distribution function in time and space. And if you would put tau equal to 1, you get this equation below. So our new distribution function just collects the distribution function in equilibrium from neighboring cells. So basically, if you want to calculate the macroscopical parameters, so density and velocity, you no longer need the distribution function, which is from the lattice Boltzmann. You just need to calculate equilibrium distribution function, which is, as we know from the one but previous slide, that this is a function of velocity and density, macroscopical velocity and density. This is quite interesting from many perspectives. First of all, so I will of course summarize at the end, but our first guess was that if we try to implement this, it will be simpler. So of course, I hear many wonderful talks here about the applications of lattice Boltzmann, which we are limiting here, of course, I'm aware of that. But our goal was not to develop the lattice Boltzmann into new applications or new more accurate studies. The goal was to actually simplify it further, as we believe that the lattice Boltzmann and its success, initial success, was because of the simplicity. So maybe that's another step towards some more simplified lattice Boltzmann formulations, because we just started this and try to get as much as possible from it. So anyway, look at the density. So density is a sum of equilibrium function from the neighboring cells here in D2Q9 formulation, and the velocity is the sum of velocities of equilibrium distribution functions multiplied by lattice vectors. Now, this is the full algorithm written in this algorithm style. So you basically, the whole solver consists of the one step, which is collection of this equilibrium distribution function from the neighboring cells, and we no longer store anything in the equilibrium distribution function lattice. So there is no LBM lattice, as we all know. I actually, looking at this algorithm, I wonder if there is any cross section or overlapping of this with some simple finite difference for Navier-Stokes, which maybe would be interesting, direction of the further studies. Anyway, so you see the simplicity of the code, and because I teach at university at the physics faculty, so our faculty does not specialize on hydrodynamics, but we have students on computational and theoretical physics, and I gave them I gave them the algorithm to implement. It was a few students, 3, and these 3 students didn't know anything about hydrodynamics. They knew more or less something about modeling and simulations, and they successfully implemented it and got some results, velocity and density fields. They changed some boundary conditions, so that was all very easy to do on the regular short CFD course. It was like 5 hours of course. And here is an implementation. It even looks simpler. It's a C implementation of this LBM. I called it LBM Tau 1. You may call it as you wish, but anyway, it's the thing is to see the simplicity. So after we initialize, it's much simpler than the BGK implementation. Okay. So now here are some results. So because this is not only about the theoretical derivation of the model, I also implemented it and run it. Here we have some basic fundamental verification studies. So we have Poisson flow in 2 dimensions compared to theoretical values, and some error analysis. So we see the slope of the error goes with size of the system, and like the power law to the -2. And so once we increase the system size, the error decreases. Now one can ask what are capabilities of the model. Here is an example of the run of LBM1 in a case of driven cavity at Reynolds number 3200. So in the title, I wrote that the model is good for the algorithm is good for low Reynolds number, and the reason is that this 3200 Reynolds number cavity flow was possible, but one had to increase the size of the mesh rapidly. So I mean, the size of the mesh is the main factor which lets you go into higher Reynolds numbers. This is because if we come back to the viscosity in BGK model, so we know that viscosity does change with tau, and once we have tau fixed to 1, we cannot change viscosity using this parameter. So the only way to change Reynolds number is to change the size of the system. And to change the size of the system is to increase the grid resolution. I found it possible to even increase further, but the time of computation was longer and longer, of course. So there is, one can say, there is no free lunch also in this model. And here is some comparison to GIA paper on cavity flow, the standard paper for comparisons. I will not go into much details because, as most of you know and probably understand now, that this LBM1 is nothing new. It's not a new LBM model. It's just a simplified formulation. Therefore, we expect it to give the same results as the usual lattice Boltzmann for tau set 1, which of course may be also done. Now here is a snapshot of time evolution of the flow. It's a special kind of visualization, but the reason is to show more on one slide. But you can see on my avatar in this Google Meet application, here is an animation from the same solver which goes for you, so you can observe the time evolution of the solver as it is time evolution, it's time-dependent solver still. Anyway, so this LBM is also capable of doing all the other stuff LBM is capable of. You can do 3D, which was extremely simple. I just put the different set of lattice vectors, and we've got this one. So this is initial step towards three-dimensional porous media. I want to do it that. And now we analyze the drop of memory that was needed for the model. So above we have the estimation of the memory needed to store one single node in standard lattice Boltzmann. So you have 2 times Q, which is the number of velocity directions plus number of the fluid fields times the number of bits needed for the given one floating number, and below you have it for the LBM set tau equal to 1, so you basically get rid of this NF. You get rid of this Q. Now, if this is true, then we have this memory drop, which we estimated to be almost 76% for compared to standard LBM implementation for in 2D, and in 3D, in the 3Q29 model, it gives almost 86%. So you may imagine that large systems with low Reynolds number flow may be calculated much larger on the given machine using this simple fix. Now, how about the Reynolds number? As I told you, we have to increase the size of the mesh, and you have this plot which shows you the stability of the solver for a given tau. So I used from tau equals 0.55 till tau equal to 1.5 even. And what I was doing, I was running the driven cavity and for a given lattice size, and if the cavity and increasing Reynolds number. So if for given Reynolds number the and at given lattice size the simulation was unstable, then I didn't plot the point. So the point shows you the larger Reynolds number for given lattice size, and you can see the scaling for each of the tau. There is some scaling visible, and I found it in another paper. There is no reference, but in the R.C.V paper I put there is a reference for the comparison, and so someone did a similar study. It's interesting that if you take the low resolution of the mesh and large Reynolds number, for instance, for tau equals 0.55, so you can see this point here, but the accuracy is not very large. So it's stable, but not very accurate. Still,
You have 5 minutes left.
Thank you very much. So this still doesn't show all the story here. You have to be aware that the stability and accuracy still are here hidden in this picture. But the tau equal to 1 is here, so you can see our case 3200 is here, and we also went above. But as I told you, so you can estimate what is the maximum size for given tau. Now, we also implemented the multi-phase algorithm for this tau and equal to 1, and this implementation is possible, but the problem is that the implementation is very slow, and you have a comparison of LBM and LBM for tau equal to 1 for multi-phase and single-phase flow, and basically multi-phase is 10 times slower. Single phase is also slower. Here we have a comparison. It's LBM tau equal to 1 on the right hand side, so the animation shows you this standard first standard test for the multi-phase Shan model, and you have the phase separation. On the left hand side you have the same with standard LBM. So this speed up is of LBM. I mean, the LBM is much faster, and this implementation with tau equal to 1 unfortunately slows down a bit. And there Michał Dzikowski has came in after I showed this talk on one local meeting in Wrocław, in CFD Wrocław. He told me he has an idea to transform the MRT implementation of LBM with the same tau equal to 1 assumption, and then using computer algebra system try to expand all this into simple. It's not that simple, as you see here on this figure on this slide. You have this raw calculated in his version, but he got interestingly, and this is very recent result, nowhere published yet. LBM for tau equal to 1 in MRT implementation using this approach is faster almost 2 times. And it was verified and implemented in TCLB code branch that Michał is working on. So basically, to sum up, so it's a simple algorithm, short in implementation, or you get over 70% less memory. Its accuracy is similar as in BGK. There are possible all extensions like in normal LBM. Possible attractive areas are low Reynolds number, large lattice sizes, and I think it's good for teaching and maybe for something else. But basically, if one wants to write his own CFD solver, maybe that's a good start. There are some minuses. I told you already, yes, the main is the slows down, and not necessarily is good for GPU because all this local stuff you have to do and entangle all things all together. So with Michał, we will probably work more on MRT implementation and try to see what happens. Okay, so that's all. Thank you for your attention. And there is a preprint you can see, and yeah.
Thank you. Thank you very much. So we have time for one question, probably from the audience. Is there anyone? Okay, if that is not the case, I have myself a question. I was wondering when you just discussed the results of numerical simulations, you, showed some velocity profiles, and my curiosity, essentially, I was wondering if you did some systematic analysis of the energy balance or the entropy balance to verify that at small scales you were indeed close to the hydrodynamical manifold.
No, we didn't do this analysis, but to be honest, it is not necessary. All this comparison between the standard results and the results given from literature and the results we have are just repetition of all the stuff was done for Lattice Boltzmann, for standard Lattice Boltzmann, because we just limited the Lattice Boltzmann standard Lattice Boltzmann formulation into formulation with tau fixed to 1. So basically, it's still the same. There is no difference on the physical and like algorithmical. From physical point of view, is the same solver.
Mine was just a curiosity to see if you verified, indeed, operatively, that in the simulations you were close to the manifold. But that's fine, okay.
Okay, I will think of it. Thank you very much.
Yeah. Okay, I think we need to thank the speaker, Maciej Matica, for this lecture, and we need to shift to the next speaker, Andrea Montessori. Andrea, are you there?
Yeah, I'm here.
Okay, can you share your screen, please?
Yeah, sure. Windows or the whole screen? I try with the whole
I have
screen.
no idea. I think you have to click on Presenta ora. Let's see if you can share.
Okay. Let me know if you see my screen.
I start see something. Okay.
Okay.
Wait a second. Wait a second. Because I just see your desktop. Yeah. Okay. Now. Okay. Next speaker is Andrea Montessori. He will tell us about wet to dry soft transitions in soft flowing crystals. So you have 20 minutes, 15 plus 5 questions. I'll let you know when you reach 15 minutes. Okay.
Okay. Perfect.
Good.
So. Thank you so much for this presentation. In this talk, I will show you some lattice Boltzmann simulations of the self-transition between wet and dry emulsion in the divergent microfluidic channel. I also will report on a route back to order, which is observed in the regime of large opening angles of these microfluidic channels, whereas a more natural trends toward an increasing disorder. So an increasing disorder from regular hexagonal droplet structures from disorder emulsion-like and foam-like structures is to be expected. Anyway, all the simulations have been carried out with a, I would say, a novel lattice Boltzmann approach for multi-component flows with the inclusion of near-contact interactions. So I will start from a very brief discussion of the model which I employed to simulate this kind of complex flows. As I said, basically the basis of the algorithm is, the algorithm which I use is based on the color gradient model. So the color gradient lattice Boltzmann model for multi-component flows. I will not enter into details. Anyway, here you can see that the color gradient lattice Boltzmann basically consists of 3 steps. The first one is basically a very basic collision step, which I code as a single relaxation time, as you can see here. So basically you have a very standard streaming and collision step with a collision which is based on a BGK approximation. Okay, plus I would say a further term, which is this phi I here reported, which is the so-called perturbation step. Basically, the perturbation step perturbations term is the add-on which allows to basically to have a build-up of a surface tension within our multi-component, but two-component system actually. So here in this, just as a note, in this equation, Fi is the ith component of the total distribution function, which can be split in two because I have two components in my system, which code, for example, for oil and water or for whatever binary liquid system. FIEQ is the equilibrium distribution function, namely a second-order expansion of the Maxwell-Boltzmann distribution. Omega is the relaxation time, as usual, which is related to the kinematic viscosity, and phi I is the perturbation step. So 2 words about the perturbation step. So the aim in whatever multi-component, two-component lattice Boltzmann approach is to reproduce, basically, is to induce a surface tension. In the color gradient, the aim is to reproduce the stress jump condition across the interface between two liquids, 1 and 2 here. And this is done in order to induce a surface tension between the two components. So the perturbation step, I will not enter into details, as I said before, but because the color gradient may be implemented in several ways. Anyway, the perturbation form, which I implemented, takes this form just to tell you that, so the source term phi is basically proportional to F, which is the color gradient actually, or the gradient of a scalar field, which is the phase field, okay, which is reported here, is also proportional to A. A is basically the coefficient which is employed to tune the surface tension of the model. So basically, once you fix and basically the relation between A and the surface tension is reported here. So A is directly proportional to the surface tension. So once you choose the surface tension of the model, then you fix A, and basically there you go. Just to let you know that this form of the perturbation term is compliant with macroscopically with the capillary stress tensor. So basically what we have macroscopically is a system of equation that is a conservation of mass and the conservation of momentum with an additional term which basically calls for the stress jump condition, which is, I mean, physically based and is in agreement, in accordance to with the correct form of the capillary stress tensor. Then, after the perturbation step, basically in order to minimize the diffusion of a component within the other one, basically we employ another step, which is a recurring step. All the details here I reported. Perhaps I think one of the most important publication in this regard, which is the work of Lattice and Rothman, in which basically you can find all the details. But anyway, the idea of the recurring operator is to minimize the diffusion and to maximize the phase separation between the two components. Okay, so now at this point, by implementing a color gradient, we have a quite standard Lattice Boltzmann approach to simulate multi-component coalescent flows. But our aim is basically to simulate dense emulsions or foam-like flows. And so the problem is to avoid the coalescence between neighboring fluid interfaces. And usually in physical systems, the coalescence between droplets and droplets or interfaces with other fluid interfaces is avoided because of the presence of, for example, surfactant or colloids, which position themselves at the fluid-fluid interface. So how we did this? Basically by introducing a local repulsive force at the interface, which basically lights up when two fluid-liquid interfaces are in close contact with each other. So basically we took the stress jump equation at the fluid-fluid interface, which is reported here, and basically we added a further term, a repulsive term, which is pi n, and this pi, which is a function of the distance between two fluid interfaces, basically, is the term which is responsible for the repulsion between the neighboring fluid interfaces. H, obviously, is the distance along the normal. Okay, so actually, by neglecting any variation of surface tension along the interface, so we don't have any Marangoni stresses, and so this term can be neglected in that case. And if we project the equation along the normal to the surface, then we obtain something like something that we call an extended Young-Laplace equation, which is reported here. Actually, the Lattice-Boltzmann implementation is quite simple because basically you have to add a further forcing term to the equation, so to the collision step. Basically, you have to find out whether you are or not on the surface, on the interface of the fluid. Okay, then you check what if you have another interface in between, in the neighboring along the normal, and then if this happens, then you lights up this. Is not a disjoining force, but this repulsive contact, this repulsive force. Basically, in this repulsive force is proportional to this parameter A, which can be it depends on the implementation. It can be a function of the distance between two interfaces, which basically controls the magnitude of the repulsive interaction. So in some sense, you can tune basically the magnitude of the repulsive force with respect, for example, to the attractive forces, which are due to the effect of the surface tension. And so you, by tuning the repulsive force, the near contact repulsive force, for example, you can tune the rate of collisions between droplets. Okay, so anyway, in our work we set A in order to avoid the collisions between neighboring fluid droplets. So, as I said before, our aim was to simulate the self-transition between wet and dry emulsion, namely from ordered monodispersed assemblies, as reported here in figure B. As you can see here, you have a cluster, a very regular hexagonal cluster, as denoted by the triangulation here, which is very, regular, and the transition so occurs between this kind of structure to a heterogeneous and polydispersed foam-like structure, like, for example, those which can be encountered in the so-called HIPE or highly internal phase emulsions or foams, for example. So, as I will show you, this transition is driven by a very subtle, I would say, competition between inertia, surface tension, and this competition is mediated by or modulated by the choice of the device geometry, which in our case is the choice of the aperture angle of the microfluidic channel. So I will show you two movies just to let you understand what is the setup of the simulation, and to show you some, I hope, some interesting movies. So this is the formation of an hexagonal pattern within the microfluidic channel. I would like to point out that this is something that we call an ab initio fluid dynamic simulation of the formation of the cluster within the channel. As you can see, we have a buffer in which basically we observe some rearrangement of the droplet after the outlet of the nozzle, and then the droplet basically far from the nozzle, the inlet nozzle, arrange themselves when the capillary number is basically low enough, arranges themselves in a hexagonal fashion, in hexagonal structure. As you can see here, the emulsion is monodispersed, perfectly monodispersed, and the outcome of the simulation is this assembly of droplets in hexagonal structure. But if you increase the capillary number, then you can observe after having fixed the geometry, you can observe a transition. Okay, so as you can see here, you're losing the very nice hexagonal pattern here, and what you have is the formation of a more complex, very not ordered, I would say, foam-like structure, as you can see here. So, okay. So before starting the discussion about this transition, I would like to talk about the phenomenology of this phenomena, so the early stage formation of the cluster within the microchannel. So let's start from the low capillary case. In this sequence, I report a sequence of the crystal formation at low capillary number. Here, the capillary number was about 0.04, or maybe below. Anyway, the capillary, an important thing, the capillary number here is the inlet or nozzle capillary number. And so it is computed basically with the velocity of the droplet within the inlet. The surface tension, and the viscosity.
Andrea, you have 5 minutes left.
Okay, I will go fast. Anyway, below a given value of the capillary number, every new droplet emerging the divergent channel push away another which is downstream and takes its place in the process. As you can see here, this process is metronomic and does not involve any breakup event. But if you increase the capillary number above a critical value, which we found to be around 0.1, basically you observe a transition to a heterogeneous dry form-like structure, and which is basically this transition occurs because of the subsequent breakup events which take place downstream the injection channel, as you can see here. The good thing is that the same pinching mechanism, so this breakup has been observed also experimentally in a very nice work of De Chiolla and Bisval. And so also the transition capillary number found in the experiment are in very close agreement with the other. So this is a good point. But let's talk about the mediation of the geometry on this self-transition. So a question which arises, what is the role of the geometrical details on the wet to dry cell transition? So in order to do this, we perform series of simulation by varying the capillary number and the opening angle of the divergent channel. And basically, we plot the distribution of the equivalent droplet diameters within the channel for each given pair of inlet capillary and aperture angle. I will go fast here. Anyway, what we found is that below a given capillary, which I told you to be 0.05, no breakup event is observed, regardless of the opening angle. And so the upcoming structure is a monodisperse assembly of droplets. If we fix the geometry, for example, 45 degrees here, if we raise the capillary number, then it is possible to trigger the breakup events, as we saw. And for a given aperture angle, the number of breakup is basically a function of the inlet capillary number. And indeed, by increasing the capillary, the droplet structure increasingly takes all the hallmarks of an heterogeneous dry form, as evidenced here. So here you're passing from 0.04 to 0.16, something capillary. Okay. We found that, as I said before, that for alpha in range of 30-60 degrees, capillary 0.1 is a critical value around which the soft structure which emerges from the simulation is an hybrid between a wet and dry foam. And if we focus on the highest capillary number which we simulated, which is 0.16, the polydispersity increases as alpha increases from 22.5 to 60 degrees. But surprisingly, by further increasing the opening angle, the polydispersity starts to recede and nearly vanishes at 90 degrees. And you can see this because basically this density distribution of the equivalent diameter is basically the same as in the first case, as in the case of 22.5 degrees. So why? Now, before tell you why at high opening angle you observe this transition to order, it is useful to understand why at small, when you observe simulation at small angle of the aperture, you have a very monodisperse emulsion even at high capillary number. This is basically because at small opening angles, the breakup processes are inhibited because the droplets are guided towards the main channel very gently. And so the slow expansion process favors the longitudinal displacement of the droplets, okay, which are steered towards the formation of an ordinary crystal in the main channel. But when we work with large angles, basically each droplet which exit from the inlet channel experiences a sudden expansion, which is responsible for a fast recovery of the circular shape. And basically, this fast expansion determines a very sudden deceleration of the outcoming droplets, which loses its, we call the droplet hammer action. Okay, so basically, what happens is that the sharp deceleration favors the cross-flow transversal displacement with respect to the longitudinal displacement. And so basically what you can observe is that the droplet slide preferentially on the downstream, basically can slide on each other.
Andrea, you should come to the conclusions quite quickly because we are running out of time.
Okay, so just to, I can skip to the conclusion. Anyway, we reported on the, as I said, on the wet to dry cell transition in dense emulsion, as originated by the geometry control competition between inertia and surface tension forces. We unveiled a counterintuitive mechanism that is the spontaneous reordering of the emulsion in high capillary numbers, which is obtained by increasing the opening angle of the divergent channel. And this comeback to the order can be interpreted as the result of a balance between inertia and interfacial forces. We hope that the present finding will shed new light on the basic mechanism of self-organization in low-dimensional structure, and we hope that these works can be a guidance for future development of functional materials, of two-dimensional functional materials based on the use of droplets. So thank you so much.
Thank you very much. Time for a very quick question. Meanwhile, the next speaker can start preparing the sharing of the slides. Okay, so Andrea, just a very quick question. All the simulations you did in 2D, but you mentioned also a comparison with experiments. The experiments were performed in 3D or 2D?
The experiments are three-dimensional, but the channels are very shallow.
Okay,
so the droplets are not droplets, but cylindrical. Yeah, droplets, but they are cylindrical. And so the 2D approximation is usable in this case.
Thank you very much. So Danilo Silva, are you there?
Yes, I'm here.
Okay, share your slides, please. So Danilo Silva will talk about collective motion of soft particles in a channel. The floor is yours, please. Go ahead.
Can you see the screen?
Yes, I see it.
Okay. So hello, everyone. Thank you for the introduction. Today, I'll be, thank you also for the opportunity to present my work here. Which is on the collective motion of soft particles in a channel, and as a PhD student from the University of Lisbon. So the particles at the microscale have been studied significantly, and it's an ongoing effort by the scientific community. And usually, by studying particles at such scales, one can separate them between hard particles and soft particles. And usually it's different type of systems involving this type of particles or droplets, for example, colloids, emulsions, and so on. Now, usually what happens when one is studying these particles, especially if one is looking at numerical simulations, people tend to, we can idealize the particles as being hard or having a very fixed spherical form. However, this is not often the case, as we have systems composed of many different types of flexible particles, and it's not really good to ignore the role that the formability can have in this type of channels. So we wonder that what is the role of the formability and what type of response we can have and study this type of flexible particles and this type of collections. For example, cellular systems like flow of red blood cells, we have very flexible systems where they play an important role. The flexibility plays an important role in the flow of the particles. So an area where the applications of this type of particles are important is, for example, microfluidics, where experimental techniques strongly converge in both for soft materials and cellular systems. And this is important because there's a lot of applications in various cell biological applications and biomedical devices like cell sorting, for example. And when we're looking at such skills as well, like microfluidics, we're usually dealing with low Reynolds number because of the micro-sized features. And again, I want to highlight the importance of cell deformation and flexibility. For example, again, bringing back the cell sorting of cells, where cell deformation plays an important role, and also for different type of geometries where we have different types of obstacles, deformation is very important so that the particles, for example, again, cells can flow easier on the channel. And there's been a number of numerical studies looking into this type of flexible particles by looking at the capillary number, at the Reynolds number, and the relative viscosity. And more recently, there's been a study looking into particles, soft particles in a channel with neutral wetting, where they showed that there is a discontinuous shear thinning as a function of the pressure difference. So basically, what happens is as you apply a pressure gradient, you have you increase. First, you have a movement like a solid block of all the particles. But as you increase, there's a discontinuous behavior where the flow of the particles in the middle is slightly faster than the ones near the wall. So these type of simulations have been done in 2D. So we want to look at this and study, again, look at the flexibility. So we can look at parameters like the surface tension and the capillary number. But again, we now want to go a step up and look at 3D systems, looking at 3D droplets. So again, we can use the Lattice Boltzmann method, where basically, again, since we want to simulate a system with particles, we can represent one fluid for the for the flexible particle, and for the other medium, we use a different fluid. And then we can recover our microscopic variables like density and velocity. Again, also we can again recover the Navier-Stokes equations, as you may well know, and we can also vary the viscosity of each different fluid. So it's important then to look at what has been done. For example, there is the model. Which has been extensively studied using this type of interaction. For example, if we want to have then two different fluids, we need the component separation given by this expression where we have our interparticle potential here, which is equal to the density, and K is our fluid, is our different type of fluid, and we have G, which is the strength of the interaction. So we want a repulsive interaction to separate this type of fluids. So we want G to be positive, so you can have a repulsive interaction between the two components. But then also to simulate the two non-coalescing and many different types, a large number of droplets, we want to have a competing mechanism. So in this competing mechanism, we have a short attractive intracomponent force, which acts on the same component and keeps the same phases together. However, if we only have that, we will have droplets, but these droplets will coalesce into one. So one can add this mid-range repulsive intercomponent force, which acts on the first and second neighbors, while this one only acts on the first neighbor of the lattice. This one acts on the first and second neighbor of the lattice. And this way we can frustrate the coalescence of the droplets, as you can see here in two snapshots of colliding droplets, where these two droplets collide. And for a certain parameter of G's, we can frustrate the coalescence between the droplets. So if there is no mid-range repulsive force, we can see that the droplets coalesce into one. However, if we do have a mid-range repulsive force, so the completing mechanism is complete, we have a frustrating mechanism, so it frustrates the coalescence of the droplets. Now, like I mentioned, since we want to go to 3D, what we did was we used higher order lattices in this type of systems. So for the same, for the new algorithm, what we used for the mid-range and the short attractive force, we used the D3Q39 lattice and the D3Q41 lattice. So these are high order lattice. So this is sixth order of isotropy, and this one is eighth order. And so these are high order lattice, and it's important also, I want to mention here that we use the D3Q41 for the streaming, because it helps reduce the spurious velocities that this type of algorithm usually has. So higher the lattice is tend to reduce the spurious velocity at the interface. So again, I show you here two snapshots of now in 3D using similar parameters of G, and where we collide the droplets. And again, we can see that we are able to have two different types of droplets that repel each other. So this allows us to go to 2, 3, and many more droplets, and a large number of droplets. So having done this, we want to make sure that our algorithm is sound. So we looked into the Laplace law, and this is done very simple by measuring the pressure difference between inside and outside the droplet. And we plot the pressure difference as a function of 1 over the radius. And here I want to highlight that we vary rho 0 in our pseudo potential. Here rho 0 is basically a normalization parameter, which is basically a free parameter. We can fix our G's, which is the strength of the interaction, and vary rho. So by varying rho, we are able to then achieve different surface tension values, which is no other way to look at it is seeing it as the stiffness of the droplet. So higher surface tension, a more rigid droplet. Also, we looked into the disjoining pressure. Of course, we need to characterize the repulsive interaction between the droplets. And what we can see here is that we simulate two interfaces separated by a distant age, and we measure the disjoining pressure. And we can see when there's no competing mechanism, so FC, we can see that the disjoining pressure goes to a negative value, indicating an attraction, so meaning that the droplets will coalesce. However, if we have the competing mechanism, we are able to achieve a positive disjoining pressure, meaning that the droplets will not coalesce. In the second plot here, what we did was we varied the viscosity ratio M, and we can see we're able to have the same advantage as the 2D model, where the disjoining pressure is independent of the viscosity ratio, which is what we wanted to achieve, because if we want to vary the viscosity ratio, we don't have to worry about the coalescence of the droplets. Now that we are able to simulate a system of many droplets, what we did was simulate a channel, a pipe, or like a tube, if you will, where we have high volume fraction, and we want to look at the role of flexibility here. So what we did was we applied a force to the system, so the system is driven by a force, and we have neutral wetting at the walls of our channel. So we looked at the relative viscosity as well, which is basically the flow rate without droplets over the flow rate with the droplets. And since we want to look at, again, study this collective motion of flexible particles, the parameters we looked at were the surface tension and the capillary number. So the capillary number basically is the inertial effects over the surface tension. So by plotting the relative viscosity against the force for different surface tensions, so for different stiffness of the droplets, we can see that we see a discontinuous drop in the viscosity. For example, for very flexible particles, so a low surface tension, requires very little force to have this discontinuous behavior happen. However, for a more stiff droplet, we need much more stronger force to have this discontinuous behavior occur. Then looking at the capillary number, we can see that if we look at the capillary number, the curves will tend to collapse into one, which again indicates might suggest that the capillary number is the primary variable that we should look at if we want to look at how the flow responds to different types of flexibility in the system. So to summarize, what we did again was we were able to expand our algorithm to simulate 3D droplets using higher order lattice. And we use this new algorithm with higher order lattice to study 3D droplets in microchannels, where we can see we can vary the flexibility using the surface tension and the capillary number. And in the future, we would like to study more active cases, or not so passive, where we can add activity on each individual droplet to be able to simulate more active systems. So that's it. Thank you for your attention. If you have any questions, please do ask.
Thank you very much, Danilo, for this lecture. We have 5 minutes for questions. So, team, please go ahead.
Hello. Thank you for the presentation. Hello. I have 2 questions, but let us start with the first, and maybe there's somebody else who wants to ask a question. You showed the decrease of viscosity with increasing capillary number, and of course it's a smart idea exactly to take the capillary number rather than force on the x-axis. The question I have is, do you observe any change in your spatial arrangement of the particles or the microstructure of your suspension? How can you explain that the viscosity is going down at that particular value of the capillary number?
So we don't see rearrangement in the droplets. So what we do observe is that for example, the droplets in the middle tend to flow a bit faster than the droplets near the wall. So since for a higher capillary number, so we have a more we're increasing the flexibility. This discontinuous behavior happens. So that's the way we looked at it. I'm not sure if that's what the question you're...
Yeah, my question was more about the mechanism, why it is happening. You have a tube flow, and your viscosity is, I presume you look at the total flux along the axis of your tube, right?
Yes, on the plane, yeah.
Which means you don't really know in which region of your tube, closer to the center or closer to the wall, the viscosity is decreasing.
No, we don't know that. We just measure the flow velocity.
Right. It would be worthwhile looking at the radial distribution of your particles, because it's also known that softer particles tend to go closer to the center line when the capillary number increases. And that is, of course, decreasing viscosity. So it could be the spatial arrangement, or it could be the deformation of the the bubbles or droplets.
Yes. Yeah, it could be there. Another thing that I also want to point out is that we have interaction here with the wall. So we have also neutral contact angle, which I've seen that, like, in some papers there show that also plays an important role. I just want to comment on that.
Okay.
Your second question?
Thank you.
Yeah, there is another question by Shaltiala Heul.
Yes, thanks very much for the clear explanation of the model. I have little understanding of LBM, so I wanted to ask about the G1 and G2. It seems that you can join the two particles by the two drops. Yes. Okay. Now, first, is it reversible? So if I start with one drop, I'm not sure if it's possible that it will separate to two drops, to smaller drops. And so, second, if it's tuned to any experimental surface tension of the particles, of the drops of interest at all, or is it just like a toy model at the moment?
Right now, I can't think of at the top of my head of experiments, but so your other question was if the droplets evaporate.
Yeah, or separate, or like phase separation from one droplet to two, like the blackboard.
Not naturally, no. So you have a droplet, and that droplet, if you leave it, it will evaporate, but it will not separate into two droplets just if it's just there. Yeah.
So do you think so? It's not reversible. Because if there's collision, there's one droplet created from two. I understand, from these two competing G1 and G2. So, and I'm just asking if it can go backward.
No, you can't do that. No.
Okay.
So there is time for another question. Probably, Tim, if you had another question, you can go ahead.
No, I think I'm fine. Thank you very much.
Fine. Yeah. Any other question? I do have myself a question, a very quick one. I was wondering if you tested the effect of confinement, if you have any claim on what would be the effect of confinement on this shear thinning effect.
We did not have a look at confinement.
What is your expectation?
Well,
at some point, you should lose the effect, I would expect, no?
Yes, I think also at some point you should lose the effect for if you have confinement. Well, I'm not really sure, but yeah, I would expect so. Yeah.
Any other question, comments or remark? If that is not the case, let us thank the speakers, all the three speakers of this session. Now there is a coffee break, and we meet back in 20 minutes. Thank you very much. Okay, I think we can start. So welcome everybody back to this second part of technical session 10, soft matter 2 in the virtual room Palma. We have two speakers today in this second part of this session. The first speaker is Agnieszka Truszkowska from New York University. She will talk about molecular dynamics simulations of ionic polymer membranes under an electric field. So you have 20 minutes, 15 plus 5 questions. I'll let you know when you are at 15 minutes. Okay? The floor is yours. Please go ahead.
Thank you. So, good afternoon. My name is Agnieszka Truszkowska, and like said, I will be presenting you work I did with Professor Maurizio Porfiri on ionic polymer simulations with molecular dynamics. And specifically, we focus on the ionic polymer metal composites, or IPMCs, which are a class of soft active materials with applications ranging from soft robotics to biomedical engineering. And what you see here is a microscopic image of an IPMC. So they consist of an ionic polymer membrane, or an ionomer. In this case, it is naphthion, and they are coated with thin metal electrodes, in this case platinum. So what is special about them is that when one applies a voltage to them, they deform, and similarly, when they deform, they produce voltage. And this is due to the unique structure of the ionomer. So the ionomer consists of fixed highly mobile counter ions, such as proton or metal ions like sodium, potassium. And when the ionomer is deformed, or when there is a field applied to it, obviously the anions are fixed, so they cannot move, but the counter ions are mobile and they move along with the water that is also present. So this creates a complex interplay between the mobile components and the fixed components, and actually the exact mechanisms for this behavior are not well understood. And it is believed that that it is related to the osmotic and Maxwell stress interplay in the ionomer. And basically complete understanding of the behavior of these materials is not possible without looking at the atomistic level. So the objective of this work is to develop a simplified yet representative molecular dynamics model of an IPMC under electric field and study the interdependence of stresses and the distribution of atoms. And specifically, we use naphthalene as our ionomer and sodium ion as the counter ion. And what you can see here is a chemical representation of naphthalene. So naphthalene consists of a hydrophobic polymer backbone and regularly spaced negatively charged side chains. And the side chains, the charge is associated with a sulfonate group. And initially, without any deformation or voltage, there will be a counter ion present near the sulfonate group. And we introduced two simplifications in our molecular dynamics model. First, we approximate the metal electrodes with smooth walls. These walls interact with the atoms through Lennard-Jones potential. And then we also introduce the electric field as a simple bulk unidirectional force. And we study two systems. In first system is fully periodic, and there are walls on its sides, and these walls are only visible to the sodium ion. And so basically the other atoms don't know that the walls are present. And in the second system, second system is actually not periodic in the electric field direction for all atoms, and similarly, walls are also impermeable to all the atoms. So in case of first system, what we want to do in both of them is to see how the sodium migration and trapping at the wall influences the vicinity of naphthalene. And in the case of system one, we want to simulate kind of like a bulk naphthalene environment, while in the case of system two, we want to look at more like a naphthalene electrode interface. And all these models are developed in LAMPS. So in the case of the first system, what we do is we first create a periodic naphthalene membrane with 7 naphthalene chains and 15 water molecules per side chain. And we equilibrate the structure, and we also use the equilibrated structure to compare it to current data in the literature to see, to validate our model. So we analyzed some common metrics like density and diffusivity of water and ions, and we obtained sufficiently close agreement with available experimental and numerical data. And then we take this equilibrated membrane and we place the sodium impermeable walls on the sides, and we apply electric field of 2 different strengths. So what we want to see, again, is migration of sodium towards in the direction of the electric field and creation of a pile-up zone at the wall. And then we want to examine how do the other atoms react to it and the stress. And we managed to achieve it in the case of highest voltage. Atoms are actually sodium ions, and you can see that in the case of highest voltage, this is a front view, there is a clear congregation of sodium ions at the wall. And in the case of lower voltage, there's actually, there is 1, 2, it's just much less pronounced. So we further examine just the ions, and it is now more visible for the highest voltage, how they change, their position change. So the gray atoms are actually initial ion positions, and you can see that they are pretty evenly distributed in the cell. And the blue ones are the final state after applying the electric field. So you can see both the pile-up, and also an entire zone when there are no more sodium ions left, and depletion zone. So we also examine water molecule transport along with the ions, and we see two things. First, that the distribution of water, initial and final distribution of water change quite a bit, which is most likely due to the rearrangements of N.A.M polymer. And we also see that part of the water migrates along with the sodium ions, and water also forms, you can see it here, water also forms solvation structure on the ions, especially visible in the pileup region. We also look at the common metrics for structural distribution, so the spatial distribution of atom pairs. And sulfur is basically the sulfur from the sulfonate group, so it is a measure of the presence of the anion, so the negatively charged ion. And we can see that in the highest field, the separation between sulfonate groups increases. And also there is less water present near the sulfonate groups, which makes sense because it migrates along with the sodium. And finally, that there is less sodium around sulfonate groups that also migrates. Finally, we examine the spatial distribution of atoms and the stresses, and we do it by dividing our simulation cell into equally spaced and equally sized rectangular bins positioned in the direction of the electric field. So we compute stress and the number of atoms in each of these bins, and then we average them over some period of time, and we plot the values for each bin as a function of bin center. So with this approach, we are able to plot both atom numbers and stresses. I will sometimes refer to the numbers as concentrations, but in this case of a small system like this, it's probably easier to look at the numbers rather than the concentrations. So what we see here is that we can see a clear sodium pileup, an increase of number of sodium atoms, and also we managed to capture the depletion zone when there are no sodium ions anymore present. And for the highest electric field, we can also see that in the case of the highest electric field, the water concentration changes proportionally to the sodium concentration. So the depletion zone and the lower sodium zone are associated with a drop in water presence, and then as the concentration increases, there is also more water of sodium, and finally it reaches a local peak in the pileup region. Sulfur is again the measure of the presence of the sulfonate group, so the negative ion, and we can see since sulfur is fixed and it can only rearrange locally, so it tries to rearrange accordingly, but it cannot really achieve it. So the changes are minor, although one can see the depletion and one can also see slight rearrangement in the pileup zone. Looking at the stresses, we see a peculiar stress pattern in the electric field direction, I mean for the component in the electric field direction, and also compression in the perpendicular directions, as well as the fact that the off-diagonal stresses are on the noise level. So to explain the stress distribution in the electric field direction, we compare it to the concentrations of different species, of the involved species, and we can see that the peak of the stress distribution, the orange peak, corresponds to the lowest number of water molecules, and similarly lower number of sodium ions and sulfonate. So we believe that the reason for the peak is the basically repulsion between sulfonate groups. So sulfonate groups cannot move and are suddenly in an environment when there is less water molecules to shield them from one another, and also less sodium ions to counter their negative charge. While the second peak is related to the pileup, and it's likely stems from simply having more atoms and more molecules in a single bin. So we perform a similar analysis in our second system. And the second system is again not periodic in the electric field direction. So we have to build it in a little bit different way. What we do is we take a single N.A.M chain and surrounded by water molecules, we then collect all the water molecules into something I refer to as water basin. And this gives us a substructure for replication. We then replicate the structure in lumps 12 times to get 12 chains. We add the walls, and then we proceed with the same equilibration procedure as we use for the bulk periodic membrane. Also, since in lumps we use the simulation cell is actually fully periodic, so to cancel the interactions of atoms across the non-periodic boundary, we use a thick enough vacuum layer on each side. And what we get is we observe two phenomena. First, we see a sodium pileup. So, and the sodium ions are also surrounded by water molecules, forming hydration shells. And we also see that the N.A.M retracts in the direction opposite to the electric field and kind of compresses itself. And when we look at just the ions and the water molecules, it is even more evident that there is a N.A.M contraction in the opposite direction and the formation of a nice evenly distributed pileup. So, but when we look at the concentrations, so the distribution of the number of atoms of each species, we see that first we see that they change proportionally. So an increase of sodium ion is also related to an increase of oxygen in water, so water molecules and the sulfonate groups. And we can also distinguish the pileup zone. And finally, when we compare these concentrations to the stress distribution, we arrive at some interesting observations. So when you look at the stress in the direction of the electric field, you can see several peaks. These peaks using the concentration distributions, but what we see is basically we see two types of peaks. The red peaks correspond to the regions when there is less water molecules and less sodium ions. And again, we believe that the peak is the result of the increased repulsion between the sulfonate groups. And the second category of peaks, the purple peaks, are actually related to simply a larger amount of increased presence of different types of atoms in that particular region. So in conclusion, we have developed a simplified but representative atomistic system properties and spatial distributions of atoms and stresses in the cation pileup conditions. And through this study, we have observed two distinct stress evolution mechanisms: stress increase due to a higher repulsion of sulfonate groups, and stress increase due to increased number of atoms in that specific region. So I would like to I would like to acknowledge the National Science Foundation grant that funded this research, and thank you all for listening. I will gladly answer any questions.
Thank you very much. So, is there any question from the audience? I do have a couple of quick questions, actually. Are these numerical simulations, MD numerical simulations, expensive from the computational point of view? And the second, just curiosity, is the ensemble that you used in the numerical simulations. You thermalize the system, you keep pressure fixed. What did you do precisely?
So basically, for the computational part, they are not horribly expensive.
Yeah.
These were all anywhere between 5 and 10 realizations, so not a lot, but they were, like you saw, the variability wasn't big for the electric field. application, and they run within a couple of days. So it is not that bad.
Okay.
And the ensembles I used were basically for the equilibration. I use a combination of MDT and NTT ensemble.
Okay.
Yes, and I follow a procedure that was published for a bulk NA-film membrane, and it includes annealing and also like a final longer NTT simulation to relax the bolts.
Okay, thank you very much. Thank you very much.
Thank
Any
you.
other question, comment, or remark? If that is not the case, let's thank the speaker once more, and let us shift to the second speaker, the last one of this session, Alexandra Pachalieva. Are you there?
Hi.
Hi.
Oh, you can hear me. Okay.
Yes, I can hear
I'm
you.
trying to start my video, but I'm not sure if that's possible.
Share your presentation.
Okay. Now, do you see me? I think you see me now.
The video I can see, yes.
Okay.
Now, let us proceed with the presentation.
Yes, yes. Entire screen, I assume.
Entire screen, yes.
Okay, great.
Okay.
Oh, sorry. No. Okay, great.
Wait a second. Let us stay on time, and we wait for 1 minute, and then we start. Okay?
Okay, perfect. Yes. So just let me know when to start, because I don't see anything.
Let's say I slowly start. So next lecture is given by Alexandra Pachalieva from Los Alamos National Laboratory. She will talk about deriving LBM collision operator using the coarse-graining MDLG approach. You have 20 minutes of time, 15 plus 5 questions. Let us say that when you are at 15 minutes, I give you a sign, okay?
Okay, would I see the sign? Because I mean, I just see
you can hear my voice, okay?
Okay, perfect. Thank you so much.
The floor is yours. Please go ahead.
Thank you. Hello, everyone. It's really nice to see you. I mean, I don't see you, but you see me. So this work has been conducted in a collaboration with Alexander Wagner and Los Alamos National Laboratory. I'm actually a PhD student at the Technical University of Munich, but yeah, I'm here right now in the US, early morning, and I would like to present you basically, Alexander gave a really nice introduction about the MDOG approach earlier this week on Monday, and I will just show you some more results from that work concerning the collision operator of the MDOG. So let's start. So I'll just hide this. I'm not sure if you see that. Oh no. Okay, no, perfect. So basically what we have, as you know, we have a microscale, which is the molecular dynamics simulations, and they're very expensive. We have also mesoscale simulations like Lattice gas, Lattice Boltzmann, and many others. And what we want to do is to build a bridge between the molecular dynamics, the microscale, and the mesoscale, like lattice gases and lattice Boltzmann. So basically, MDOG is a coarse graining of a molecular dynamics simulation, and I find it as a very interesting approach to find interesting physical properties of different systems that cannot be obtained using the hydrodynamic limit. So everyone knows about molecular dynamics. We actually approximate a real physical system, and what we're doing, we track different atoms, which are described by the Newton's second law. I mean, this method is very successful, but because of the humongous amount of particles that we need to simulate for a real system, it's really difficult to obtain nice results or anything useful for the applications, even with the current high-performance computing technologies. So this is the main reason why we go forward to something which is a little bit more feasible, like lattice gases. I mean, they're much more cheaper than molecular dynamic simulations. Basically, they're cheaper because we constrain our particles to follow a certain velocity, certain path, so it's in a discrete system. And basically, we have our density and momentum equation, which are given over here. I don't know if you see my mouse. I hope so. So, and this lattice gases, they're described by this evolution equation, and usually N.I.s, these are occupation numbers, which could be, at early times, lattice gases were, the occupation numbers of the lattice gases were Boolean numbers. Later on, there were different lattice gases which use integer numbers, and that was pretty a breakthrough because it's fixed a couple of problems of the lattice gases. And here, this is our collision operator, which also conserves mass and momentum. Lattice gases are fully fluctuating models. They have humongous statistical noise, and that's one of the reasons why they are not so useful. And in high dimensions, we have to consider many collisions, which could become really cumbersome. So since my talk is about over-relaxation, so I will throw to you some interesting ideas that our group, Alexander's group, has developed. For example, one of his students, Thomas Blommel, he worked on integer lattice gases, and he was trying to achieve, like to understand the model better, and he realized that lattice gases, in this sense, integer lattice gases could not show over-relaxation. And he had to perform double collisions, which were not physical, but it was a really interesting idea how to look at over-relaxation. And I think that was actually the first idea that came after that. Okay, why not? Why not look at over-relaxation and in our MDLG approach? After lattice gases, they came this lattice Boltzmann simulation. So basically, you take non-equilibrium ensemble average over these occupation numbers, the integer occupation numbers, and you obtain real numbers Fi's and real collision operator sigma I. And in this case, the Boltzmann evolution equation is described like this. Everyone knows it, I think. And this is already a deterministic collision operator. So the lattice gases, they were probabilistic and noisy, but here we have something that is deterministic. Usually, the best, or not the best, the easiest approximation for the collision operator is the BGK approximation. This is the single relaxation time. Here I have given the form for multiple relaxation time, where basically we have this lambda matrix, which contains all the relaxation factors depending in which direction or with what kind of rate actually our distributions are relaxing. And of course, this is very like simplistic description. Still, we have certain conversions from moment space from normal space to moment space, but at the end of the day, we conserve mass and momentum, which corresponds to the continuum and Navier-Stokes equations. So basically, Lattice-Boltzmann is very simple, has 2 steps, streaming step and collision step. Everything else is, boundary conditions, forcing terms, and so on. But that's basically the whole idea of the method. Further on, because we are talking about over-relaxation, I want to just present you this concept. What does it mean? So in the simplest collision operator, the BGK collision operator, we have just one relaxation time. And the relaxation time also takes hold to the viscosity of the system, where the viscosity is really interesting. Here, theta is 1/3 usually in D2Q9. And what we have here, if you think a little bit harder about this, when we have very low viscosities, we have a problem. And this problem could be solved basically using over-relaxation. But let's say first what kind of different versions we have. So this is actually a figure from Tim's book. So this book, it's a really nice book. Please, just a short advertisement for that. So I use it because it gives a perfect explanation how the relaxation depends on tau. So if we have the relation tau over delta t equal to 1, we have full relaxation. So our Fi's decay directly to the equilibrium distribution function given here. On the other hand, if we have this relation tau over delta t between 1/2 and 1, our solution will oscillate around F equilibrium. So this is actually this really huge gaps, really oscillating things that you see. Sometimes these oscillations will lead to no convergence. Sometimes they will converge, as you see here in this grayish line. So actually, we could achieve even faster convergence using this. And the most, I would say, boring time is like when we have under relaxation, when Fi decays exponentially. I mean, that's something very physically clear. That's this dotted dashed line with huge dots, which just shows the decay towards F equilibrium. So please take this in mind. I'll show you some results about for over relaxation and under relaxation later. So yeah, stay with take this slide in mind. Next, everyone could ask, okay, why after having so many different mesoscopic methods, like why do we need anything in addition? Why do we look at coarse graining of a molecular dynamics simulation? And it's a good question, but so what we want to achieve here is we know that the molecular dynamics simulations are the ground truth. So they're always valid, and we can simulate almost every physical system that we can think about using molecular dynamics. However, we cannot simulate a huge humongous system. So we would like to obtain certain physical properties and use these properties for modeling mesoscopic model, which would be, in our choice, the Lattice-Boltzmann method. So we are trying to reconstruct to get an informed idea how to construct the Lattice-Boltzmann method using a molecular dynamics simulation. And this can help us in various fields. For example, when we look at fluctuations, which Alexander showed on Monday, that could be very useful, and we can find different correlations just looking at the displacements and the probability distribution functions. In addition, for simulations like with small scale, we cannot really use the hydrodynamic limits, so we are forced basically to go towards microscopic description like molecular dynamics, but still, I mean, this is very difficult. For example, for shale problems, you need some certain external information, and this can be obtained using the molecular dynamics lattice gas. And how do we do that? So we have a molecular dynamics simulation, save the displacements and the positions and the velocity of the particles. So as you can see here, Alexander also showed this figure before that. So we have our positions, and with certain time, our atoms will displace to a certain other position in our field. And actually, we want to track this displacement, and that's to do this. We overlay our molecular dynamics simulation with a lattice. And then we look, okay, from this time step to the next time step, where did our atom went? And doing this, we can define, so basically that looks very similar like the lattice gases. We can define our occupation number, and so Ni xt is the current position, and x plus Vi and T plus T delta T is the next position of our particle. And using this correlation, we can obtain a collision term. And by rearranging this equation, we can find the molecular dynamics lattice gas evolution equation, which is given by this. So basically, MDLG can measure average properties of their underlying physical system, and this is really exact, like we are just coarse-graining a molecular dynamics simulation. Okay, and this is lattice gas, so bear in mind, Ni's are occupation numbers. If we define a non-equilibrium Boltzmann average over these occupation numbers, we can obtain again, as in lattice Boltzmann method, our FIs. And we could do this also for our MDLG collision operator and obtain a MDLB collision operator and write the MDLB evolution equation. One interesting and important paper for this work is Parsa et al. He found the global equilibrium distribution function. I won't go into detail about this, but we use his work in order to find or to describe the F equilibrium. It has really interesting properties, but you can refer to the paper. Basically, it's obtained using an equilibrium distribution function, and we sum over all the positions where our particle went, and we find our occupation numbers and average over that. So MDLB, unlike MDLG, it's a deterministic method, and it's free of fluctuations and noise. So we can look at it as a lattice Boltzmann kind of method. So next question is how to approach and how to find our collision operator. Like what's the form of the collision operator? As we know,
Alexandra, you have 5 minutes left. 5 minutes. Okay.
We see different collision operators, and okay, how do we do that? So we take the MRT collision operator, the basic form. We have a matrix with a certain size. We'll look at D2Q9, and so we choose certain moments. I won't go in detail about this because I don't have time, but we look at different moments, and from these moments we can obtain the collision operator. Okay, this is not really important, so I'll skip this slide. This is just the transformations backwards, forwards from momentum space to normal space, and how do we obtain the relaxation rates. So in order to get nice statistics, we need a nice, simple test case. And this would be, in our case, the simple shear flow, because it's a symmetric system and we can average in time and in space. So this is the simple shear flow. Actually, it has to shear till the end, but I didn't manage to get this. And let's go to the results. So we simulated that. We obtained our moment, our collision operator. So basically, this what you see is a collision operator. So these are the contributions in different cases. So pre-collision and post-collision. And as you can see here, these colors, so basically this is a little bit dimmed because it's after a collision, but actually green and green, they match. So we have something like an under relaxation. So that's what we measure from MDLB. And the next, this was for ballistic regime. And in the next slide, I'm showing you the diffusive regime. So we have much larger time steps. And here we can see that the streaming, like the pre-collision, post-collision, and the post-collision and post-collision is here, and pre-collision step are actually, the colors are shifted. So they absolutely shift with 90 degrees. So we call this over-relaxation. And what we think that's the reason why we see this is when you think about a ballistic regime and a sheared flow, you can see that in ballistic regime, basically we don't have any collisions, and basically the flow follows the direction, the particles follow the direction of the flow. So we'll have this kind of displacements of the distribution function. However, in a diffusive regime, we have many collisions, and the particles will be more chained into these collisions, and they will have basically no memory effect from which direction the shear flow goes. So they will flip their sides. So these are the displacements, what I'm showing you here. So basically the displacements will go in the opposite direction, which is very counterintuitive on the first glance. And we calculated also the relaxation rate from the MDLG, and we still don't understand completely how, even in this very simple shear flow, how this really relates to the over and under relaxation, but we're trying to map this to a certain theory. What we see is that the behavior of the relaxation time can be seen as a function of the time step, and basically it has this function. But I mean, this is a little bit preliminary results actually. So that could be a very interesting plot when we understand it completely. So if you have any questions, we can talk about this later. I think I'm over my time. But let me give some outlook and conclusions. So basically, we have measured, I mean, this flipping of the collision operator, as you saw in these colorful graphs, this shows the over-relaxation from the lattice gas. So this is the first lattice gas, which we can say it over-relaxes. So over-relaxation cannot be just seen as a numerical trick that we use in order to have low viscosity, but actually as a physical property, which comes from the coarse graining of the molecular dynamics simulation. We have seen, we saw this non-equilibrium distribution of displacements. We can calculate them, and we can also calculate the MDLG relaxation rate, which we still need to understand better how it relates to the over-relaxation, under-relaxation cases. What we want to do further is to do machine learning on this subject, parallel implements, and use MDLG for different physical phenomena like fluctuations, boundary conditions, multi-phase thermal models. Like it can improve significantly our understanding of these phenomena. So I would like to conclude my talk with thanks to first to Alexander, and he's in Fargo, and it's always super nice to talk to him over Skype. I want to thank my supervisor at the lab, Kipton Barris, and one of our colleagues, Nick Lubers, in here. And I want to thank Sky because she always brightened my day. I mean, that's Alexander's dogs, and it's always really nice to see her around. Yeah, thank you so much for your time, and I hope you enjoyed my talk. I'm open for questions now.
Thank you very much. I think we have a time for one quick question. Tim, please go ahead.
Thank you very much for the most interesting presentation. I like this idea, going from the microscale to lattice Boltzmann. What came to mind when I saw your slides, you make the assumption quite early on that you have a relaxation, right? You have Fi minus Fi equilibrium. And that is, of course, as we know, it was one of the key steps in the development of lattice Boltzmann to make everything more efficient and so on. But in your analysis, do you see any signatures that a simple relaxation process may not be appropriate? Or in other words, would you expect more complicated collision operators that don't rely on a superposition of simple relaxations to be required in some regimes at least?
Thank you, Tim. That's a really good question. So basically, single relaxation works pretty well for many problems, right? We are simulating right now a simple shear flow, so it's very difficult to see much more dynamic in our system. I mean, it's very simple flow. As you know, you just have the shear rates, which you can see, so the diagonal elements that you saw in these colorful graphs. However, we have seen previously, as Alexander mentioned in his talk, that Thomas Global, he basically in his, now if I'm not typing it wrongly, but he basically saw that the collision operator of his, the equilibrium distribution function, and also Parsa, Reza Parsa also saw that actually the collision operator resembles pretty closely the entropic lattice Boltzmann collision operator, not collision, equilibrium distribution function. The equilibrium distribution function from the entropic lattice Boltzmann method proposed by Carlin. And that was something we're looking forward. So we think that basically we'll need much more information, like more interesting test cases to sample from and to coarse grain. But basically, we think that we could even end up with something which is velocity dependent. It could be so Tim, your question was about the collision operator, right? Yeah.
Yes.
Sorry, I just yeah. So yeah, we think that we would see something very similar. We're open for all the different possibilities, but we think we will see something which is closer to the entropic lattice Boltzmann method, because we have seen this previously. But it could be all different kinds of relations coming into play. I mean, I think that BGK, the single relaxation BGK approximation is very very useful because it works. But actually, I think beyond the scenes, some more interesting physics is happening.
Okay, thank you.
Thank you very much. There is another quick question from Ellen Vesper. Ellen, please go ahead.
Yes, my question would be, could you use our DSMC instead of molecular dynamics? Because when I understand you correctly, you use only repulsive collisions and no attractive forces between your atoms, and DSMC would model the Boltzmann equation accurately and still would give you over-relaxation and would be probably faster than molecular dynamics.
I think that's a good, very good suggestion, just to see. So I'm not really familiar with the DMC in detail, but I assume that. So you suggest to use instead of the molecular dynamics simulation? Is that right?
Yes, it is like a simplification of molecular dynamics. Where you split the movement and the collisions, and that is faster because in molecular dynamics you really have to resolve the collisions, which is the collisions are also calculated in DSMC, but we don't follow the exact path.
I see. Yeah, I think that would be an interesting thing to try out. So why we went for the molecular dynamics is because we just wanted all the physics that's there. So we didn't care about the cost that will be caused by simulating molecular dynamics simulations. And we just really wanted to look at the complete dynamic, so beyond hydrodynamic limit. I assume that if we need to try this on more like less expensive model, we could try DNC.
Thank you. Yes.
Okay. Okay. Thank you very much. I think we had enough questions. Let me thank Alexandra and all the speakers of this session. The next appointment is for the dinner talk at 18 by Luciano Rezzolla. So thank you very much to all the speakers again and to all of you that attended this session. See you later.
Thank you. Thank you, Lisa.